Good morning. Let's start chapter 30. I'll describe why it is true that the orbital radii of the orbiting electrons in hydrogen are quantized, restricted to certain discrete values. I show in the broken line an orbit of hydrogen, radius r, and show the matter wavelengths wrapping around the circumference in such a way that a whole number of them, an integer number of them, fit neatly around the circle. The condition for constructive interference is that the distance traveled, in this case the circumference, must equal an integer number n times the matter wavelength, the de Broglie wavelength. You may recall that the de Broglie wavelength, also called the matter wavelength, is equal to Planck's constant, h, divided by the momentum of the object, in this case the electron. So lambda is h over mv. What we would like to do is obtain an expression for the allowed orbital radii in terms of the quantum number n, which can be 1, 2, 3, 4. As many different n's that there are, and there are an infinity of them, that's how many different radii there will be allowed for the orbiting electron in hydrogen. We want to obtain an expression for r, the allowed radius, in terms of constants of nature, listed here: Planck's constant, the mass of the electron, the charge magnitude of an electron, and the electric force constant. All constants of nature will not change ever. What can change, however, is the allowed orbital radii corresponding to the chosen value of the quantum number, sometimes called the quantum index, n. So we begin with this equation here, which contains the r that we're interested in, and the quantum index n, and various other quantities, some of which are constants, m and h, pi, of course. But there's a variable that changes from one orbital radius to the next. It's the speed of the electron. In order to obtain an expression from this equation involving r in terms of only the quantum index n, and all or some of these constants of nature, we have to obtain an expression for the speed v in terms of r, so that then we'll have an equation involving only r and the various constants in this table. All right, our goal then immediately is to find an expression for v, the speed, in terms of r. And to obtain that, we turn to Newton's second law, F equals ma. The force in question is the pull by the proton at the center of the circle. That's the nucleus of hydrogen. It's the pull by the proton on the orbiting electron. The electric force between two charges, the force that one charge exerts on the other, follows the k, q, q, or r squared rule. There's your k, there's your q times a q. Remember, the q's in the force law are absolute values of the charges. One charge at the center of the circle is the proton charge E, and not shown is an electron orbiting. Its charge magnitude is likewise E. So we have the force is k e squared over r squared. And on the right side, we've got ma, the mass times acceleration term in Newton's second law. Well, there's your m. The v squared over r is the expression for the centripetal acceleration of a particle moving in a circular path of radius r. This equation involves multiple constants in the box, k and e squared and m. It also contains the special thing we're looking for, the variable r. It has the v that we noted back here, must be obtained in terms of r and any other constants of nature. Well, this equation can be rewritten, solve for V. You'll get an expression for V in terms of M and K and E and R. I won't show what that expression is. It's not so very important. I just need for you to know that it is possible to rearrange this equation to solve for V in terms of all the other letters in this equation. When you obtain that expression for V, put it right back here. And then the final result, after you rearrange and solve for R from this equation, after you replace this V with the expression you'll get here, this is the final result. You have inside the parentheses a boatload of various constants in variable quantities. Planck's constant squared, pi squared, the mass of the electron m, the electric force constant k, and the charge of a proton or electron squared. When you substitute in the various values in this table for those various quantities in the parentheses, the number shown here, 10 to the negative 11, in meters with an n squared outside. We prefer to work, when we're dealing with the hydrogen electrons, in distance units that are angstroms. An angstrom is 1.0 times 10 to the negative 10. So if you rearrange this equation in terms of angstroms, you get this final result. It's called the quantization of orbital radii equation. We take the liberty of subscripting the r that's here, adding a subscript n to remind us that the r that we're looking at will depend not just on the constants in the box, but also on the quantum index n, where n can be 1, 2, 3, 4, 5, and so on. Final result. We'll put this equation to use in a later lecture when we quantize the energies of the electron in hydrogen. More is to come.